updates? Oh, we are live. Yeah.
We are live.
Okay.
Yeah.
What updates do you want to discuss, Rajan?
Okay. We will discuss our website because Christopher has changed the website. Allow everybody. Thank you for. We have changed. We have modified.
There's a lot of interference, isn't there?
Let me check whether there is interference.
Sometimes. Oh yeah. Okay. Sometimes when I'm talking, we get like feedback or something. So.
Okay. Right now there is no feedback, right?
No, there isn't. It's good. Okay, we're good to go.
Okay. So what we are talking about is our updated website. So I'll start from here. Essentially, it's about the same. We are not changed anything much. But the speakers we have changed. Some of them have dropped out. They couldn't make it. But rest of us, like myself, Christopher, Laszlo, and Emmanuel are there. We are the main speakers. But also there's invited speakers. So let me go to the next. Committee also is changed a little bit. We have kind of shortlisted ourselves, and then three of us are here in different positions. Then the schedule, the venue has changed. So let me before we forget this. So the contact is same, Dean's Budapest. So we go back to our original venue, where is a Dean of Budapest. That's right now. That's our venue. It could change if you find something closer and probably a little more IT aspects available. We may change that either on the 29th or that day. But we will keep informed. Right now, it's Dean's from Budapest. So that's what that's a home base. That's where we start from, and then hopefully, we as of now our live streaming will start from there, and it is on the May 30th. That's the same thing. It may be subject to minor adjustments. That's a good point. That should not. Then the same thing. 9 to 9:15 talked about our speech, like Christopher may introduce, and then I will start talking about 10 minutes, 5 or 10 minutes. Then Christopher will start presenting his talk. That's the same, but that extends. So he starts the keynote address, me chairing, 9:15 to 11. So it could be slightly flexible in the sense that.
Yeah, I think there could be like we could have like maybe a break in between, and then.
Yes.
Yeah.
So this may include some break, and also Laszlo has half an hour. So Laszlo may take up some 15 minutes from here, something like that. We may adjust according to what.
You have an hour. So what did you say there, Rajan? Laszlo has half an hour.
Half an hour. So he may need like 10 minutes or 15 minutes more if we need. We can start a little early. So we can take a break at 10:45, 5 minutes break, and then he can start.
The schedule is like it's a kind of a plan, but maybe it's not like.
Yes.
Or do you want me to go in and like fix those things and make sure that they're.
Yeah, you if you can make it, you can make that 10:45 and then 5-minute break. 10:50, Laszlo will start, and he will.
Yeah, fair enough.
11:30, and then.
I'll just sit down and think about it and make like appropriate changes and.
Okay.
No problem.
So then 11:30, 12:30, about an hour, which means I may present up to 45 minutes. Then we may have a Q&A. If the Q&A gets over, we will start our lunch earlier. I mean, we'll go for lunch even at 12:25.
Okay. Yep.
And then, so we have enough time. We come back by 1:25, hopefully. And then the Emmanuel will start. And he wants some adjustments. I think, Christopher, you are making some adjustment for his thing. Because you already made?
Yeah.
You already made the adjustments, right? 2:45. So 1:30 to 2:45. So hour and 15 minutes. So he and you are already asked Emmanuel about Valamandas. So if you want to present during that time. So 2:45 to 3:30 is when Dr. Kurle will start talking. So again 45 minutes. Then 4:30 to 5:15. So we have 45 minutes. Again, flexibility is good here. We may take a break if necessary. Instead of here, you can take a break here necessary. But
We can see what you're looking at, Rajan, but
oh, I'm sorry. I should have put. Yeah, I had to start all out. Sorry. I thought I was. Yeah, this happens all the time. I'm glad that you guys are there to point out because.
Pretty good. Yeah. Okay. Yeah.
So let's start again. Okay. I had to repeat again. Sorry. So what I was talking in audio essentially is this one. The about is about the same. There's no changes there, but speakers have changed.
Well, actually, there is changes in the about page.
Okay, so you can point a good thing.
There's the hotel was changed from NH Budapest to Dean's Home Hotel Budapest. Also, there was
no. In this one, is there any change here?
Yeah, TEGS will be held online from May 30th. On May 30th, and broadcast from Dean's Home Hotel Budapest, Hungary. That's a big change because originally it was in a conference hall in NH Budapest Hotel.
Oh, yeah.
And also, if you scroll to the top of the page, you'll see there that it says from May 30th to 1st of June. Now, the schedule still talks about going to the 1st of June, but that's mostly like sightseeing and stuff.
Yeah.
It's not actually part of the conference when you think about it, but
but many people put like that. Yeah, many like in the IC Fast, they do put like this about sightseeing and all. There, it's part of the.
So that is there, and people could join that. But obviously, the conference is going to be mostly online in that case. But obviously, sightseeing can't be online. Although, Rajan, are you still planning to go to CERN? How's that going?
Yeah. So one of the things is after our thing on 31st, we have the hop in hop off at Budapest, and then we'll have a small dinner. But I have to leave early. I will be leaving 3:34. We have to come to Deanburg. I have to collect my luggage. Then I go to Brussels, via Warsaw Pact. I go to Brussels. Then I spend the Sunday, essentially Sunday, Brussels, going to Atomium, different places there. So I'll be spending the evening. I fly to Geneva. So I go to Geneva, and that hotel is not too far, about half an hour, and they have, I think, shuttle and things like that to CERN.
And so are you gonna live
Monday? Yeah, Monday, the whole day I will spend in Geneva, CERN. So I hope to, the whole day is available for me. I don't know what I can see, but I plan to go there and see whatever I can, they allow me. And then Tuesday morning, I fly back to the US.
Yeah, I'm just wondering about your CERN visit. Are you going to live stream that, or are you just going to...
Yeah, whatever they allow me to live stream, I will do that.
That's true. Yeah, there might be restrictions.
Brussels also. Brussels also, I will try to...
You're underground. I don't know how much reception you'll get on the...
Yeah, that's the problem. So I may take only photos. Right now, I on the conservative side, I will have photos, and we can post the photos.
Video underneath.
Yeah, videos,
and then you can post them to the website if you want, or not to the. You can upload that to YouTube. I could do that for you.
Yeah, so I will, whatever I get, I can hopefully through WhatsApp. I'll get all that, and then I'll then automatically upload to our WhatsApp. From WhatsApp, you can probably upload.
That's a great idea. Okay, so let's continue on here. Everything else is the same.
Again, donate.
Click the donate button, Raja, and okay. Don't. No, go back.
Yeah. So you can donate paper.
Yeah, do donate. Yeah, why not? Yeah.
So whatever you can put either with PayPal or credit card or whatever, debit, you can do that. Okay. Now,
let's move on. Speakers.
Move on to speakers.
Right. You're going through the whole site here. Okay, yeah.
So again, myself, Christopher, Laszlo, and Emmanuel, we are the main speakers. But Dr. Kudile is there, but he doesn't want to put his thing. He'll just present it. He's a well-known person in their circle. The committee, again, there's a lot of some short listing here. So we
Yeah,
three are here.
there's a lot of repeated names on that, but
Yeah.
as you can see, I've made all the corrections there, so I think everything looks good.
Yeah.
Yeah.
So we are okay now, and then we move on. It's nice that you put a donate button in all the pages. That's a great
Yeah.
thing. Okay.
And
So
there's a register thing there
yeah,
as well, but I
the
don't know if the
schedule. Yeah.
registration really doesn't really function as in the sense of the conference is now online, so to
Yeah.
register is a bit pointless.
Yeah. So again, the important thing is about schedule. Again, it's the same thing. Christopher will start. He's the MC. So then he introduce, and then I talk about the whole conference and the people. And then Christopher will start presenting his keynote, and he's going to adjust this. I think 10:45. He may make it 10:45,
Yeah, I'll
and then
adjust that. Yeah.
about 5 minutes break probably there, and
Yeah.
then so Laszlo can start at 10:50. So he'll have about 50 minutes, 40 minutes. Sorry, 40 minutes,
So
and then I start 11:30, 12:30. So again, I may not
well,
finish
wait a
my
second.
talk
Laszlo's going to have a half an hour
plus 10 minutes.
plus. So yeah, I see what you mean. Yeah. Okay, great.
Okay.
Yeah.
So I probably will finish at 12:15 about my talk, then about 5 minutes, depending on the Q&A, 5 to 10 minutes. So by 12:20, 12:25, we'll go for lunch because I think we go nearby place, so it should not take that much time. But we come back at 1:25 about, so that we are ready for Emmanuel's presentation. So Emmanuel is going to present. Hopefully his friend, his associate Velamendas also will present. So they have 1 hour 15 minutes. That's all he wanted. It's only 1 hour presentation. So
Yeah,
15
that's
minutes
right.
Q&A. Yeah, he was talking about that.
And so
Then 2:40. Yeah.
Everything else is correct except we could put a break after Curle's.
Yeah. 10 minutes, 5-10 minutes here. And then so we have enough time here. So then
Yeah.
we'll have
So then we'll finish up around 3:30 instead.
yeah. So yeah, we can adjust this time because we have enough time between that and the closing ceremony. But the panel discussion will be in the form of a general discussion, essentially.
Yeah.
So that's one thing I want to point out. And then we have this closing ceremony where
Yes.
we already have the hotel booked, everything. So
Well,
whoever
the
want to join us,
Yeah, it's like a restaurant.
Indian restaurant, where we
That's
get
right.
both vegetarian, non-vegetarian. I am not a vegetarian. But then we'll finish our any social entertainment, general discussion, things like that. So yeah, we have a couple of hours there. And so we have enough time. And then next day morning, we start our hop-in, hop-off.
Yeah.
And that's it. So I go in the evening, like 3:34. I should go. I have to get ready to go to airport, go to Dean's Budapest, collect my luggage, and then I think Laszlo and probably you may come with us. I come with whoever want to come. Laszlo, he said he want to take me to the airport, but we'll see. I think we may meet. You said you may meet when I come there at the airport. We can adjust that. That's not.
Yeah, I could probably meet you at the airport as well. Yeah.
Yeah. And then when going back, Laszlo will come with me if you want to come with that, or if you want to continue with hop-in, hop-off, that's fine too. Either way is fine. But I had to come back to. Oh, you may have to come with me if you have the key for Dean's Budapest, but I don't know.
I don't know. I'd say you'll have a key.
Yeah. So I can collect my luggage and then that's a good thing. So I don't have to put it anywhere. Also, I can put the luggage at the front desk and then just collect it from there. That may be faster. We'll see. We'll play according to the hour there. So then, but I had to be at the airport, I think, by 5:30 or something. My flight is around 7.
Okay. Yeah, we don't need all the details.
Yeah. So then I go to Brussels. I see the Atomium, things like that. And then from there, that's on Sunday. Then Sunday night, I go to Geneva. So Monday night, I plan to spend in CERN. So that's the important thing for all the people. And then, we'll take photos or videos possible. And we'll post it here, later on. So essentially, Christopher will continue there. And then Laszlo will be with him Sunday, probably. and then so that's our briefly our
Okay.
idea, and our contact here is Technet. Are you? I think I'm not able to log in. I don't know why I cannot see this one. But I think Christopher will probably keep track if anybody is putting it there.
Yes. Oh, I've had a look. Yeah, there's so much.
Okay. So
Okay.
then again, the address of Dean's Budapest is our home base now, and then but actual presentation we could change depending on Laszlo has a better place. But that's
True.
mainly in a gist. That's essentially what our modified thing is. I think we are all set.
Yeah. So it should be good. We'll have we'll have good speakers. We'll entertaining, and obviously Emmanuel's. There was a bit of an announcement there. I don't know if you saw it on the emails with something called the Zitter Institute. Was it?
Oh yeah, it's interesting.
Did you see that?
I can pull up that. Let me check. That's
okay.
Interesting.
Yeah. So I'll just let people know anyway. So it's something to do with Sabine Hossenfelder did some video.
Oh, he sent this one, huh? Did he send this one? Who sent this one? Zitter Institute sent to us.
Zitter Institute, yeah.
They sent directly to me. I don't know why.
As well, yeah. Maybe you're signed into their newsletter, are you? So
I don't know. They may know that I am watching, her things. So that may be the reason. So let's go here.
Yeah, that's it. Yeah.
On May 4th, Sabine published a video. New theory explains electric force as part of gravity. Allegedly, it says allegedly. I don't know. In this video, critically reviews and co-authored by Kovacs, member of Zitter Institute. Autonomy of publication. Members of the Zitter Institute publish their research independently. Use don't necessarily reflect on the institute. Sabine is a respected voice and he appreciates critical thinking, contribution, opportunity. About the criticism, concern is that she sees a serious mathematical mistake and conclusion. So the conclusion may not be accurate. From that point of the authors issued a formal reply. So their clarification is that strongly objects claim that electric charges travel at the speed of light. Correctly point out no massive particle can reach light speed. However, there exists a theoretical hypothesis suggesting that electrically charged particles possess an internal rotation motion at the speed of light. This concept emerges from the Dirac equation itself, referred to as Zitter-Bohm. In the 1933 Nobel Prize, Dirac stated, from the electron, which seems to us to be moving slowly, must actually have a very high frequency oscillatory motion, small amplitude superposed on the regular motion to appear to us. So, result is oscillatory motion. Velocity of the electron at any time equals the velocity of light. It's a prediction which cannot be directly verified by experiment, since the frequency of the oscillatory motion is so high, amplitude is so small. But one must believe that consequences of theory, since other consequences of theory which are inseparably bound up with this one, such as the law of scattering of light by an electron, are confirmed by experiment. The foundational purpose of the Zitter Institute has been to explore and support this interpretation, Zitter-Bohm, and study its implications. So that's their main.
Yeah, if you go to the Zitter Institute website as well, you'll see. I think the link is at the top of the page. Not the very
this
top.
One?
Or
this one?
Maybe it's there. And if you scroll down, even once it loads, scroll down a bit, and there's Markula.
Oh yeah. Oh, okay.
So he must be by Oliver Consa. So he must be part of that institute, I guess. So he'll be delivering his talk on gravitons, and so that's.
Yeah, this is H1,
oh,
H4. Oh, this is what he presented in our thing also.
Yeah, he's presented that before, so it's good. And then, of course, Laszlo, you'll be doing planetary erosion, which is very unique, and I don't think anyone's really done anything like that before, have they, Laszlo? It seems to be kind of new stuff.
Yeah, he has some more new things. He yesterday suddenly brainstormed him. I mean, he got a what he called a eureka moment yesterday when he was biking. So he
and
came
before
up.
yesterday also, you Christopher, you will have opportunity to verify if my brainstorming was good or only a brainstorming, false brainstorming. Because
Okay.
at the NASA it can be very well verified, and you have ability and capacity, and you are very well trained in this case to verify it.
Okay, yeah. So where did this brainstorming
and that is about the forming of planet from the sun. It can be well demonstrated that the example, the rocky planets like the Earth, Venus, and Mars was formed from sun. In case of Jupiter and the exterior planets, I think it's something else, and it is close to the actual theory of the planet formation.
Yeah, right. Okay, yeah, I understand. Okay, that's interesting. Because there was something else there, but the point you were making. Oh, sorry, sorry. I was gonna ask a question.
I have had very, very hard days in last 4-5 days because the pre-existed description of the planet erosion, it was not very well elaborated, and that is why it was necessary to build up again. And perhaps today evening I will send some question to you to verify, and perhaps you can give me some suggestion if the presentation is the step of the presentation is well made or not, and good. And I will ask something, some question that perhaps some steps it have to present it in a small form, because I don't want to extend the presentation, because it is a very large subject. In the article, the writer before, it was in a small part, but actually it become a large form, and that is why it have to shorten it in some parts.
Okay.
In time of presentation, because example, the erosion, the ordinary erosion which is written in the geological books, I think it not need a big presentation, and some theories which is very well taught in the schools, and only we have to concern on the presentation, what is very important in this case.
Yeah, I mean, yeah, I think I mentioned that to you, that Rajan, you've done a lot of work on erosion, haven't you? And
corrosion, more corrosion.
Okay, right. But could corrosion, and I suppose corrosion, what's the difference? It's more chemical based, is it, rather than
electrochemistry.
Yeah.
So people thought it is bacteria acting, but it's not. We have proved. That's one of the first things we learned in corrosion in the master's program. One of the first things that even bachelors I learned that initially people thought some bacteria is eating up this iron and things like that from rust, but proved that that's not true. It's electric, like a battery, it's like inverse battery.
Oh, yeah.
It's like a battery type.
Interesting.
Action.
Okay, so I don't know if that would be. I mean, you're doing planetary erosion, not planetary corrosion, right? So
yeah, there's a connection, but that connection is more symptomatic, more philosophical than scientific. You know.
There could be very interesting things to look into there, and obviously, you know, Laszlo, you do more than. You've got more research than this. You're doing research into lightning and gravity and a lot of different areas. So but by the sounds of it, you're just going to focus on this one topic, is it, for this presentation? I think, did we lose
Laszlo? Laszlo?
Yeah, I think we lost him. He's frozen.
Is he frozen?
I believe
Laszlo,
so.
Can you hear us?
Yeah, he's frozen. He might be back now. He's back, I think.
Yeah.
Well, okay, so by the sounds of it, it's just he's focusing on one topic, so that's good. And then Rajan, your topic is kind of more eclectic, isn't it? You've got
something happened. Something happened.
Yeah, he's dropped in. We'll see if he might rejoin.
Yeah.
So in the meantime, while we're waiting for him to rejoin, you're doing work on superluminal condensates, and you're also looking at Hodge PDP. So that's with, of course, John Hodge, who's
yeah. So mine. You know, I'm expanding a little bit, but I think I may have described. Actually, I can show on the other screen. It's kind of a right now. I don't know whether I'll have time to convert, but I'll show my research on this recent one. I was thinking how to start the whole process. You know, so I can start from the particle in a box, because that's a standard thing that people know of the quantum physics. That's the key thing in quantum physics, is the particle in a box. So let me see. Let me first pull out the slides. I mean, I will be able to put in the slide, but it's written rather than you know, graphic thing. The handwritten. So I have to do some graphics as possible, because again it is a little bit messy. So let me put this. Yeah, I was looking at the wrong mouse. Okay, wondering what happened to this mouse.
You want to just add that?
Yeah, I just add. Oh,
I already did.
Oh yeah, thank you. Yeah, I was removing. I saw what I'm doing.
What?
Okay, right now.
And then this.
Okay, good. So I think I had to focus on this is.
Oh, wait a second, that's not working. Hang on a sec. I'll put this back here. Maybe how does it? I've forgotten how this works. Actually, you kind of go like this. No. Okay. So yeah. Okay. So that doesn't work on this. We'll have to just do it this way. Just solo.
Yeah. Oh yeah. There it goes. There it goes. Okay. So very simply, I'm just showing here. This is a particle, and this is supposed to be a box. So it's 2D version of the box.
Yeah.
But normally, what we say is that the particle can be here anywhere. So this is where the quantum mechanics come to picture. It can be anywhere, but what I'm saying is geometrically asymmetrical, in the sense that the particle is here. It's different from particle is here. It's not the same because of the walls. But if you remove the walls, we get something. The particle is isolated. This is like a vacuum. So here, particle can be anywhere, and it will be symmetrical. That's the idea. But the particle here, inside here, now if you use general relativity, is this a particle has a mass?
Yeah, but Rajan, what if the box is circular?
Circular again, even if it's circular, near the wall is different. You see that
because Because you have a singularity there.
Yeah. Whereas inside, the geometry is more three-dimensional, whereas near the wall, it is restricted. It has more freedom here, but no freedom in the wall at the level of the wall.
What about quantum tunneling?
Yeah, that's the thing that people are talking about, quantum tunneling, but that's a different subject. I'm saying in terms of symmetry.
How is that a different subject? Are you talking about a particle?
The reason is that we assume that, and then based on that, we develop a wave function, and then we say that
the
wave function.
The sides of the box are infinitely tall, isn't it? So the particle is doesn't have the energy to get out.
Yes.
Okay.
So, but in the ultimate level, yes. I mean, in an ideal situation, we can say the wave function does have a component even outside the wall. So even, if we solve that problem, but we have to solve it for the vacuum, and then we have to adjust for this one, and then we saw that so we have to come up with a vacuum solution. That's what I'm saying. So then we say, okay, there's a wave function. This wave function can go, can tunnel. It has a component outside, like a mirror. Here degenerate states, so it can tunnel through that because degeneracy, same energy levels, it can tunnel through the wall. So that's a very important aspect. Whether it will solve the Schrodinger cat problem, I don't know, because if it tunnels that, can we sense it outside somehow? That wave. So that's the question. Okay.
Well, the particle can never tunnel out of the box, though.
Not a particle, but something about the particle, information about the particle. Oh. If it tunnels here, can we get some information about how the particle is, where the particle is?
I think the whole point is that it can't tunnel because the side of the box is infinite.
Yeah.
It would need infinite energy, so it doesn't have that. Okay.
So that's why the vacuum solution is important. So if it's a vacuum, then we have this particle, and this particle can be anywhere, and it will have the same symmetry, same wave function everywhere. So this, according to general, so we can bring in the general relativity here. Actually, we talk about general relativity. This particle has a mass, so it will warp or bend the space around that, and it will create, because of the warping, bending of space, it will create a gravity locally. This gravity will cause it to collapse, like, depending on the direction. Usually gravity is towards the center. It will create a micro black hole. So this particle becomes a micro black hole.
Wait a second though, Rajan. I mean, like, wouldn't you need to prove that mathematically or something? I mean, because what is the mass of your particle? How is it gonna? Doesn't a particle need to have like a lot of mass? Where is it getting the energy from?
Yeah, it has. So it's a Planck level. It's a Planck level. So that's why it's a micro black hole, not a macro black hole.
Oh, so what's the difference then? I mean, surely, like when they're making micro black holes at CERN, yeah, or they were concerned about it.
Yeah.
Okay, so that was about smashing particles together, and you're giving them such high amounts of energy.
Yes.
And that energy and mass are equivalent, so the particle could turn. Actually, in the case of micro black holes, is it a particle turning into a black hole, or is it a group of particles? I suppose it could be either or, could it?
Yeah. So there is a possibility it has degenerate states. So they all collapse together, the wave function of the degenerate states, and this collapse is the one that causes the micro black hole.
But there's a difference between the collapse of the waveform, the wave function, and the collapse of a star into a black hole. Those are two different things.
Yeah. So this is not like a star. So it is. That's why it's not a real black hole, but it's a micro black hole. It's a quantum black hole, quantum Planck macro, we can say.
Oh yeah, okay. But I know that. But like the collapse of the wave function just states, well, we know the position of the particle. Correct?
Yeah, only after the collapse. So it occupies a specific place only after the collapse. So until then, it has different possibilities, right? There's many, So only when it collapses, then it has that you can measure. There is a one place like electron. It's like you can think of an electron.
The collapse and the measurement are one and the same thing, aren't they?
Yeah, when you measure, it collapses. That's the idea.
Yeah. So, I mean, I don't know. You know the way there's this whole thing about a particle can have no extent in space because if it did, it's actually kind of related to that Zitter, or the Zitter Institute thing, the Zitter thing. I don't know how to say that German word, to be quite honest with you.
Zitterbewegung.
Yeah, except in German, W is pronounced as a V.
Yeah, but that's right.
I think you've got it right. So that's Dirac's work. So, but so they were saying that if you had a particle with like a classical radius or something, then any waveform moving across the surface of that particle, for example, or the spin of the particle would have to be higher than the speed, faster than the speed of light. So in order to you know, solve this problem, because nothing can go faster than the speed of light, they decided that the particle must be infinitely to have no extent. So it's like, you know, there's no width in the particle. But this, you know, so these are just things that they've come up with to solve problems. But it is interesting, isn't it? Because I think from where you're coming from, you're looking at the particle is like a little ball, isn't it, of something? It has a diameter like the classical radius or something, and then so you're saying that after it gets energy from somewhere, you still don't know where that's from, but let's say it gets more energy. You're saying that the ball will collapse into like a particle of no extent. Is that what you're saying?
Yes. So
isn't that? But don't you feel that kind of like because we have different, you know, the way there's the different views. There's the Bohr atom which looks like a solar system. Then you have the cloudier atom.
Yes.
And then you've got all of these different kind of like if you use the cloudier atom, I've forgotten what the technical term name is, but it doesn't matter.
Electron cloud density of states.
Yeah, the electron cloud. So that'll do. So, but if you were to apply that to you know, like chemistry, where you have two atoms, let's say the hydrogen atom or something, and
proton,
the H2O molecule or something, where you've two hydrogens and an oxygen there, and then but they're connected at a specific angle, which is like 30 degrees or something like that, maybe 60 degrees.
120 degrees. 120 degrees.
That's it. Thanks. Okay, so, but like for that angle is very precise, and chemists need to know that specific angle in order for their equations to
the microwave happens because of this angle. Yes, the rotation.
Yes. Okay. Interesting. So then this cloud idea has to be modified in some way, so that they would have to happily just go back to the Bohr atom because it makes life easier, that model. But and then we have this third thing where, well, there's actually, you know, and they also like the idea of the electron radius and a little balls that are orbiting other balls and connected to balls otherwise. Little but then the other point that we're talking about is this idea that there are no little balls. They're just like, they're even smaller than that. They're already really compact. So by the sounds of it, if you're going to posit this, you're kind of throwing out the, you know, so we know that there's always contradictions within quantum mechanics, the wave function and the particle, and things can exist at the same time. And so and then we have this multiplicity of ideas of like the solar system model versus, you know, of the Bohr model versus the cloud one. That those two seem to contradict, but depending on your use case, like what level you're working at, whether you're working in chemistry or subatomic, you know, they can have different applications. But here, what you seem to be suggesting a kind of another one on top of that, another duality of states that can exist, that could also be real. But I'm just wondering, you know, first of all, you might need to justify why you're doing that, but more important, or well, just as importantly, how the two things can exist without contradicting one another. Although, you know, obviously that's open to interpretation. Or do you feel that this is necessary, or is it just a model?
Yeah, yeah. I try to make a small calculation possible, other wave function. But the main thing is that what I want to bring in is that where does it come from? It comes from a superluminar thing, which has monopoles, right? The monopoles have very high, extreme amount of energy, right?
Right, but where are the monopoles, though, Rajan?
Yeah, they are floating around in the superluminar thing. So initially, we may have, you know, the monopoles. They have their own area, like a north monopole here and the south monopole.
Oh, okay. Well, but the monopoles in the APC model, yeah,
they are going superluminar speeds.
You know the anamorphic perspective cosmology model, right? And you know where the monopoles are in that they're shining out of the projective point, and they shine through the fourth dimension, and then through the hypersphere onto the tangent plane. And when where they intersect with the tangent plane, that point, because the monopole is a straight line, yeah, and it twists, and that the point of intersection through the plane is the particle. Yeah,
that's interesting. Yeah, so we have something common there, but the thing is that
it just sounds like what you're talking about the same thing, but you're using different language. Is that right?
Yes.
Right.
I will talk eventually in the time domain, but you are talking in space domain, like you are 4-dimensional.
Well, no, but hyperspace. I mean, there would be time. There's time in the domain as well. It's just when I say 4-dimension, I mean 4 spatial dimensions, whereas you would mean 3 plus 1. So they'd say like 5-dimensional to make it. I just don't like using the term 5-dimensional. I think it just gets confusing. I mean 4 spatial dimensions. Yeah.
Yeah.
Okay. Yeah, but time is still a part of this 4th spatial dimension, you know. But everything's happening instantly because it's a torsion of the monopole, which is transmitting the information. So that information is able to go from the projective point to the hypersphere and down to the tangent plane, all in an instant, you know. So it's superluminal, right?
Yes.
In that sense, but I don't think it's breaking any of the laws of physics.
No, it is not. Yeah, that's the whole thing. So I think we will amplify this aspect later on. I think that they're very important. Magnify this particular aspect because the time and the space come together because of this particular reason. But what I am eventually do is I pull out the time aspect and say that the time tensor can because time is described by.
Wait a second. I just want to stop you there. So let's say you have this monopole, yeah, and it's spinning.
Yes.
It's spinning and it's also projecting through the tangent space, is like poking through. So you can imagine, like, let's say you get a wooden stick, right? And you push it down like onto a bed, like with a bed sheet on it, and then you begin to rotate that. You're going to start twisting the sheet, aren't you? Into like a spiral or like a vortex.
Yes.
So you can imagine that this monopole that is pushing down into the fabric of the tangent space and also rotating would generate your vortices.
Yes.
So the density of these vortices depends on what? The speed of the rotation or
how it intersects. So it is the probabilistic aspect because they are doing randomly, right? So probabilistically, you get a distribution. Like I show in my thing about, if I can show briefly, let me try to pull out this one. presentation here. I think that's part of the our initial thing. So let me pull out that.
So it's in your presentation, is it?
Yeah. So this one is,
yeah.
Emmanuel made this one. I mean, our publication. So this is here, our, the different places where it can, for the magnet monopole magnetones, can exist in different places. They are vorticing, right? They are vorticing here. So that's what I think. What you are talking is same, essentially the same thing. It's vorticing in different places. This vortex, what I'm saying, they combine together and form the micro black hole, essentially. So
okay. So you're talking right. I'm still on the
Yeah, no problem. Yeah, continue. Yeah, please continue.
So it sounds like all particles in the universe then are just cross sections of magnetic monopoles.
Yes.
Existing in it. So that's weird, isn't it?
Well, what happens is that the monopole cannot, they are superluminar. But what happens is the north monopole and the south monopole eventually come together in the random fluctuation, and they suddenly locks in and forms the dipolar. We call it Horde, dipolar Horde. Once it locks in,
well, actually, Emmanuel has a different version of that, doesn't he? That the two monopoles come together to form the
graviton.
No, the Horn Torus model of the electron, I think it is. So he's saying that the monopole was stretched and then it just comes together to form the particle. I would have a different view that the monopole exists, but it is, well, actually, see, this is where, because I'm just coming up with ideas here, but they might be incorrect. So why would a monopole extend into the fourth dimension as a long, thin line? I mean, doesn't that go against the whole concept of a magnetic monopole? It should be in 3 dimensions, shouldn't it?
Well, actually, it doesn't have a 3 dimension. That's the whole thing. It's not a real particle. The monopole is not a particle, but it is just a field. It's just a field.
No, the magnetic monopole is, if I'm not you're right. It's not a particle, but
it can be called
it's meant to be a field within the 3-dimensional space, isn't it?
They can call it unparticle or what you call partons or quasi-particle. Different terms are there.
Yeah,
I will call it unparticle.
Yeah. Well, I mean, the way the original formulation of Maxwell's equations used quaternions.
Yes.
And so it always had this 4th dimensional aspect to it. But then I think when Heaviside and Gibbs got involved, they decided to take out the 4th dimension because it wasn't needed or something like that, and they could explain everything in nature just using the 3-dimensional space. So I don't know, I mean, maybe the 4th dimension is like literally not needed. You can just dispense with it and it makes no difference to the equations. Or you see, it seems like a bit too much of a reach that I would be correct in thinking that monopoles are this long line that stretches through the 4th dimension, and that so maybe what I'm talking about are not monopoles. Then they're something else. They're magnetic monopoles, and in that instance, we're talking about 2 different things, I think, possibly, because if magnetic monopoles are like part of 3D space and they live in 3D space, then they cannot be the thing I'm talking about, right?
It's superluminar. They exist only in superluminar phase. They don't exist in real space. The monopole.
Yeah, I'd agree with that. So it seems to me that we are talking about the same thing, but I'm just wondering if we can use the term magnetic monopole to describe this thing then.
This one?
No, the thing that we're talking about. I don't know if we're able to use the
term. No.
Maybe what we're talking about is something that's different to a magnetic monopole. Maybe it's
this one. Here it's not magnetic monopole. It's not really. It is.
we're talking about the thing that you're calling a magnetic monopole, and that we spoke about, and we said, right, we're talking about the same thing. But I'm wondering, is that actually a magnetic?
Oh, the line that extends to the tangent space. Yeah, that's something we have to rethink about that.
Yeah. So these are
I'm
things.
not sure.
It's good to discuss these things, and you know,
I think we have to amplify. Yeah, it's a very good point.
Are we actually talking? You know, so instead of just saying, yeah, okay, we've got the answer, we can move on from that. It's
no, it has to be debated.
Really analyze everything and make sure that what we're saying it makes sense in the world. Otherwise,
we may have to make some calculation or something to actually figure out.
Okay, so what's next here, Rajan?
Okay, so that's the main point. So then I bring out our the main thing is here. I come back here, and then using this, we can come up with the theoretical foundation where I talk about this the matrix that I solve the problem.
Okay, so what have you got here? You got like these upper and lower indices.
Helmholtz decomposition. So this is the vortex field, which is a rotational field, and this is the 0 point, which is a translational.
You see the way you've got mu nu as an upper indices or something.
Yeah. So you have,
and then you've got G or is it?
Yeah, G is the gradient. So this is the gradient field.
Oh yeah. So you've got so what is it? One is up top is contravariant, is it? And bottom is covariant, or is it the other way around?
Yeah, it is spinning, going up or going down, essentially.
Oh no, but what is the definition of contra and covariance?
That has to do with in the G mu nu.
Yeah.
We have the upper indices versus the lower indices.
Wait a second, just to interrupt you there. Do you have like the metric tensor here or the Einstein tensor? Is that part of this or is it not?
It is not. It's totally, it's not.
Oh, okay. So it's not involved. So these covariant, because you know the way I was reading there that the contravariant is like a vector, whereas covariant is the field. Is that it?
I can pull up this thing. Hold on. I'm trying to see whether we can come up with the.
Why do you have or comma nu mu nu and G?
Oh, okay. That's to differentiate between the gradient and the sense. The mu nu essentially gives a sense. You know what I mean?
Oh, okay. So what you're doing here, Rajan, is not ordinary in any sense, yeah.
Yeah.
It's not conventional mathematics, or because like a sense field. So wait a second. It's to.
So let me. You're talking gradient, covariant, right? Covariant. You want to talk about covariant?
A gradient, though, is what? Is a field, right?
Yeah, it's a straight, like a translational field, almost.
Yeah. Okay. So you got covariant could be a field, and contravariant is the other one. The kind of how something moves within the field, like a particle or some sort of matter. I mean.
Yeah. So the covariant and contravariance of vectors, right?
Yeah.
Well, okay. Covariance, contravariance describe how the quantitative description change of basis. Okay. So you have
you're changing the way you're looking at something.
Yes. So
some geometric object.
So let's see how Euclidean vector goes through. I'm trying to see a symbol way. Okay. In Einstein notation, quadravariant components are denoted with upper indices.
Yes.
Covector, cotangent. Okay. So contravariant. Covariant are so lower indices are the covariant, the upper indices are the contravariant.
Yes.
So you have a matrix that connects between the two. You can connect the two through a matrix.
Right,
So
which is just the thing that. So you, let's say the Einstein tensor or something, you'd multiply that by one object, and then you get the other one back, and then you can multiply the other way around, and you get it goes the other way.
Yes. So you need a matrix in between.
You have the inverse or whatever. Like, it's not really that big a deal. Yeah.
No, it's not a big deal.
It's not a big deal.
I have shown in one place where you can easily simplify. So you can connect with a matrix.
I mean, there's a lot going on with these equations, though. Like, think about how many kinds of equations there are, and so it is pretty complicated at the end of the day when you start applying it.
See, it's called metric tensor. So the metric tensor does the job. Convert from one basis to the another basis. You know? So
so you're not using that in your equation. You've got something called you've got two different fields. Then do you have a gradient field and a sense field?
Yes. Actually, it's essentially.
What are your contravariants?
Okay, so one of them is what we call a linear field. The other one is a rotational field.
Okay, so why would they be fields though if they're contravariant? Wouldn't they be?
They're fields.
Are they directions within the field or something like?
Yeah, any field you can decompose. That's what a Helmholtz decomposition is. Any field you can decompose into two parts. One of them is the straight field or the gradient field. The other one is a rotational field or the vortex field.
Okay, and so
Rajan, excuse me. The field, I think the field are two types of field. One is a fluctuation field, waving field, and another the rotational field. The constant static field we doesn't have.
I think it's to do with this thing, isn't it? What are these called, Rajan? These tensor, it's like if the electric field is going this way, or no, sorry, if you're moving this way, isn't it? And the electric field is going this way, then the magnetic field will be that way. They're like orthogonal indirect motion or something.
Yeah.
So the point is, right, but that's still, they're just directions within the field. So you're still talking about fields, which would that not be covariant then? Shouldn't that be lower indices?
No, it can have.
Unless you're talking about a particle that's conductive within the field or couple,
Yeah, when they combine,
it's rotating because of its interaction with the field. Then that would be contravariant, wouldn't it? The motion of that would be Maybe I'm wrong. I'm just trying to understand.
Yeah, that's an interesting point. So I think the main thing is that suppose you are light, the photon, right? You can consider light maybe easier to consider because we know that the magnetic field is orthogonal to the electric field. We know that for sure. It has been proved. So we know that polarization. But the magnetic field can be the gradient. It can be the one that is what I call is a straight field, and the electric field can be the one that is rotating. Okay, you can also have electric field as the straight field and the magnetic field rotating.
All right.
So these are the two possibilities. So one of them is rotating, the other one is straight down. So because suppose I have a positive and negative terminal, I have a gradient, a potential gradient. This gradient means essentially a potential gradient between the positive and the negative charge, right? Now, if I have a solenoid and a magnetic field rotating in that one, they will start interacting with each other. They will have interference, right, between them. The rotational magnetic field will start inducing a electric field orthogonal to it, which will affect the actual potential gradient. It will change the potential gradient. And on the other hand, if you have a magnetic field, north and south pole, right? See, and we have a rotating electric field. That rotating electric field will produce a magnetic field, and that can interact with this north and south pole. It can increase the magnetic field or the magnetic potential, or decrease it. You know what I mean? So this is a very simple electromagnetic thing we know for sure. We can actually do a solenoid experiment. We can easily prove this. I mean, people have proved this. This is how a motor works and things like that. So you have external field, acting on it, which affects the original field. It could be a magnetic or electric field, depending on how we do. So you can have a rotating electric field, like a
the whole point of like when you use the covariant and contravariant. So if covariant is the field, and the contravariant part is like, the thing moving through the field, maybe, then those would be two different things.
Induction, like an induction could be covariant.
Oh, okay. Well, yeah, but isn't the induction, like magnetic induction, is like a magnetic field turns into an electric field?
Yes.
And an electric field turns into a magnetic field.
Yeah.
So those are two different fields that are turning into one another, which would be a bit like if you had a gravity field turning into an anti-gravity field, let's say, and back again. Or so, two different fields. But isn't the whole point of like Einstein's equations, they've got, you want to know like how a body moves, like, because the mass is creating the field, isn't it, in Einstein's equations? And the field is telling the mass how to move. So there's this reciprocal kind of thing. But don't they use tensors to describe the electromagnetic force as well, don't they? They have T mu nu. So okay, right. So that's that makes more sense to me now.
Okay. So I asked whether induction, electromagnetic induction.
So for the electromagnetic stress energy tensor, you have like whatever, the gradient of mu, and then you have T.
They say
EM, which
they say it's possible.
Which is a contravariant thing, and then ensuring the. Yeah. Okay. It's interesting. All right. Yeah. So I'm still
Lorentz transformation. Yeah, it's a Lorentz transformation.
Which is what? Sorry.
See,
so the Lorentz transformation is about time dilation, isn't it? And
no, it talks here. It's nicely written here.
Oh yeah, I should read that probably. In the context of covariant electro. Yeah.
Let's see.
Can alter covariant to contravariant tensors, but each transform from frame to frame according to the Lorentz transformation applied to. Oh, okay, right. Well,
that's what so I'm correct. I'm correct in my thinking. I was not sure. So this proves that I'm thinking correctly about this one.
Right, that seems to be correct. Yeah. But another way I was looking or taught to look at it was that you go like covariant means that something is.
No, you could be right. I mean, it's a more general thing. See, there's one person I saw he's changing. There's a technique to change upper index to lower index. So he continuously is working, creating Christopher symbol and all that. You're a Christopher symbol, right?
Yeah, I know.
It's a very important part of the whole thing.
Yeah, it's interesting. All right. So, okay, so that's kind of what you're doing there, and you.
Yeah.
But so you can just invent this new field, yeah, sense field, and then put in these upper indices or whatever, the contravariant, and so you're saying it's a rank 2 tensor, isn't it? Because it's got 2.
Yeah, indices. This will be rank 2. Yes.
Okay, and so let's say but it's a rank 2 tensor in how many dimensions then? In 4 dimensions?
So yeah, yeah, it can have any number of dimensions, right? So let's go back here.
Oh, okay.
Oh, I have to go to my sorry.
You have presented, isn't it?
Yeah, presentation. Yeah, that's what I was like. I know I got off. Let me go back here. And yeah, so you have this 2 by 2 matrix, right? Yeah. But it can have more than 2 dimensions. I mean, it's a rank 2.
No, sorry, Rajan. You know, I mean if you've got this mu thing, the upper covariant thing, then that is a rank 2 tensor. So that E mu would just focusing on the covariant or contravariant indices at the top, the mu, that indicates that if we just looked at that up by itself, would be a rank 2 tensor, wouldn't it? Okay. Okay, so and all of them have the same rank, but then they also have a third. They also have a third. They have a lower indices as well. So would that mean that they're higher than rank 2?
Yeah, that's interesting. I didn't, I didn't because I don't think it's that's important, but it's interesting to consider the mathematics of it. Going to more, if you do more microscope, going to the aspect of so they two together can form fractional dimension.
Okay, but so how are you combining them? Do you have to multiply them, or you just take them as a separate?
Yeah, it's a normal procedure of manipulating. Normal procedure that we use for the matrix operation. So I go through. I go through the paper. I go through the whole thing, finding the.
By this vector form, is it down at the bottom to do it?
Yeah. So this is you can convert into a Ket and Bra matrix, and actually in our paper, I go through the complete thing. Actually, it is a little better than what is there in the literature because I simplified because there are confusion about how to find the eigenvalue, things like that. So I go through them, and if you use that procedure, you will get that. So I can pull up that paper, our paper, which is the original paper.
Okay, but if you were to take like, I don't know, the discriminants of that matrix, yeah? Then you would multiply G E whatever that is, epsilon sub with the lower indices of G mu times G mu or epsilon with covariant mu and then G at the bottom. So you'd wind up with what at the end of that?
Okay. So this is the paper. I just run it briefly. So if somebody wants this during the time.
Well, wouldn't you wind up with just E2G or something like that?
Epsilon? Yeah, there is a metric tensor we need between them, right? Between the covariant and the contravariant, we need like a matrix.
Yeah, but I think you can multiply two things if they've got and if they got upper indices and lower indices, they'll just cancel out. They're the same.
Okay. So let me see.
So if you're trying to get something like, what were you saying there? The eigenvectors, aren't they just going to cancel out or something, or what's going to happen?
Yeah, let me show very simple. If you have lower indices like E mu nu. In order to make this upper connect with the upper thing, I have to use E mu nu, and then E mu nu. I think something like that if we have to do. Can you see that?
Yeah, I can make this bigger.
Okay. So
yeah, exactly. But there you've got two different terms, don't you? If they're both epsilon, yeah.
Yeah. Then you need something here to bring it down. This is kind of metric.
Right, but let's say they were both epsilon, like they are in your matrix, yeah, your Helmholtz matrix. Then, if you were to multiply those two together, the indices would just disappear, wouldn't they?
Yeah, I show here. I use standard technique. This is a very standard technique.
What would that even mean, though, if they were to disappear, though?
Let me see. So I convert this, right? So I get eigenvalues, characteristic field. So you have to use this one.
Okay.
You have to use minus lambda and then solve for lambda.
Oh, okay.
And then that's how we get eigenvalue. This is a standard technique. This is a standard technique.
Oh, yeah. So
A minus lambda I equal to 0. This is the characteristic equation. So this is very important. This is the key thing.
Okay, yeah.
So I show very clearly. So if you use this technique, you can solve this problem. Just follow. It's little better.
That's straightforward, all right. So is there ever a time where so if you multiply, so you're doing it, and then those two things will just cancel out like it was a usual quadratic equation.
Yes.
Things cancel out.
Yes.
Okay.
So then you get that value, and So we are not assuming anything. It's just a mathematical manipulation. Technology. I mean, it's a standard technique.
Yes, of course. Yeah, it's been done many times.
So these are all very. I spent a lot of time to ensure and also make it a little better than what is there because it's confusing. Here, people want to really understand this. If they go through this technique, you can just apply it directly for anything, for this kind of calculation. Because I did a lot of research on this.
Okay, well, that's good. Well, we're not going to go too much longer here, Rajan, because
you want to save some time, right? Yeah. So I just want to point out that, and then we can knock it off anytime because we can save some live streaming hours. We used about hour and 15 minutes, I think, little over hour.
Yeah.
But we are enough.
Continue on for a bit. That's just
we can enter the stream anytime, and then we can go, without the stream, then it won't be charged, right?
Yeah, exactly. Well, we don't actually have an account with them, so it's just
okay. No, but you are given certain.
If you want to set that up, you can, because you could just.
It's okay for now. Yeah.
It's all right for now, but anytime you want to do it,
you
can.
Yeah.
Okay, well, that was interesting, Rajan. Thanks for that.
Probably it's a very important part. Yeah.
It's worthwhile if you go through that again that'll be part of your
presentation. Yeah.
Yes, so we'll get to talk more about that then as well, which is good. Okay, in the meantime, I'm gonna sign off anyway. I'm gonna go get some food. But nice to see you guys again.
Thank you, Christopher. So next week, if Laszlo has presentation, he can practice that. I think we went over presentation kind of, so it should be okay. Then we can upload, Laszlo. We can upload to your computer either before or or 28th or 29th when I come there. Also, we can upload.
I can do that. Excuse me.
Wait a second, Laszlo. All you need to do is just email your presentation to me, and I'll have it.
Okay. No, today I will summary. I will send you the presentation of the planet erosion, and I will discuss what problem I have with it.
Oh yeah,
because
yeah.
exist some problems because as I told before, it have to be eliminated some parts because it will be too long if I am trying to present as it is need example because
Yeah, yeah. I think
in
Marshall,
the original paper
Topic and stream.
and
how much time do you need actually, Laszlo?
I have only the scheme of the presentation. No.
What is that? What do you mean? Like it's like part of the presentation, or
Yeah, draft. Yeah.
Only immediately.
So how many slides would you have roughly? Or how many do you expect to have?
Only I have a example of the primary part of the presentation, and after it I made a sketch of the presentation. And today in time of cycling house, I have speak about the presentation without that it is existing a very form of the presentation as we present in the school when we teach the children. Only like oral presentation, simple oral presentation. Because
right.
yesterday I made a sketch, and today in time of cycling I considered, because I needed 1 hours and 10 minutes to get house. I considered that the time is long of the presentation, and only the only more than the half part I have presented in time of cycling, and one important part it was not presented. Example, the demonstration of the phenomenon, which is example is very well formulated by the theory of the exploded planet theory, because the exploded planet theory is approximately similar theory, and that is good in this case, because I can use his demonstration, and after that we need to have the present the prediction of the planet erosion theory, because it minimum has 5 or not 5 points of prediction.
Really? Okay, that's good.
Perhaps as I am thinking, and 2 is connected to the which can be verified by NASA instruments.
Okay. Very good. So you've got predictions, experiments, and yeah, those are generally the key things that you need. Okay, well, so you got about a half an hour to present, and then you'll have questions. Is that enough? So okay. Okay, so that's good. I mean, if you need more time, we can possibly do that, but by the sounds of it, that you'll be able to do that, yeah, half an hour. Sure, give it a go anyway, Laszlo. See how you get on. It will all be perfectly fine. I'm sure in terms of time. We'll work something out. Okay, guys. I might see you next weekend then, or
yeah, next weekend. Yeah, next weekend is important.
What were you thinking? Oh yes, right. Do send that on, Laszlo, then, and I'll check it out, and I'll give you my thoughts and any pointers that I have, and then next week, if you want to present it, that'll be fine.
Yeah.
We'll have a
because that will be our last one before we meet. you know.
Oh, okay, great. Okay, so it'll have to be a short one then.
Yeah.
Next week. Okay, cool. Well, I'll see you then.
Okay. Thank you very much. Have a nice week. And then, yeah, we'll communicate through WhatsApp, whatever is necessary, you know, anything else comes up. But I think you are going to update the website, what we talked about. And then,
yeah, I will. I'll make a note of that and I'll update it.
Yeah, I think everything else is, I think, on track, I think.
I think so.
We'll touch base next week about everything.
Yeah. Well, we got there's a lot of other things to discuss, but that'll be after the after the conference.
Yeah, after our project. Cool. Yeah. Thank you, Christopher. Have a nice week. Thank you.
Thank you.
Thank you.
Okay. So last
Rajan, excuse me. As I have looked into your presentation, I think I have written something down in connection to it. Example on the micro level, particular level, the space is not like in case of our space. The space is somewhat condensed space. Do you know? And another thing that
so what do you mean by that? What do you mean by
example, that? Okay, immediately. And whole in case of the micro level, without other particle, we don't have. Example that we need something to have around these holes. Example, you can imagine in case of the surface of the Earth that how on the Earth surface we have holes, and or in the and when we have vortex in the water. And such a things we have to consider in case of the micro level.
So it will be like a hole.
Example, when if you look on the water.
Yes.
Example, marine water of the river water, and there exists a vortex. Something similar things existing in micro level, but there is not a plane surface. Example, in a spherical space.
So
and
that's what. If you look at here, let me show again that picture. If I show here this picture here. So this is
and like what you have inside the
there's nothing.
And what is the exterior?
This is just a vortex
I think
it's like a hole here.
But it's correct. It's correct. But something have to exist in outside of the vortex.
So let me go to the pen and paper. 1 minute. Let me get out and show the other one. So I will show pen and paper here.
I will send you a picture. I have made something, and I will send you.
Yeah. So let me show
what about I am talking.
Okay, let me show you. Yeah, I have it here. Oh, this one, yeah. Okay. I have to show it here. So in this one, we show that the vortex will be like that, right? So it is rotating. So here you have a hole.
You can make a bit bigger. I can see well.
Okay.
Because do you know my eyes is wrong and I am not looking on computer. I am looking on cell phone.
Can you see now?
No. Yes. And
so this is the vortex. This is the vortex. So you have the rotation here. So what happens is here creates a hole here, right?
And the vortex, what is it? Where the vortex is?
It could be water. It could be in the vacuum, anywhere. Let's say it's a water.
Rajan, excuse me. In vacuum, we can have vortex. We have to have something to have vortex. In vacuum, we have vortex, but the vortex is have to be causes from something.
This particle here. This particle here.
Yes. Okay. We have to have a particle. It's correct. We have to have a particle.
This particle creates this hole. This particle.
Particle. But the particle. Excuse me. The vortex have to appear in the particle space. The vortex, the particle is, it has a space. Do you understand? Every particle in atomic level have a space, and in the space we have the vortex. If the spin of the particle create vortex, because the sphere of the particle is moving same with the particle. Perhaps it has have a other spin, and every changing of the particle motion creates changing in each sphere, and in such a case appears the vortex.
Yeah, this is a spinning particle. What we say is that the spinning.
Yes,
I will call it a spinning particle.
Yes, every particle is spinning, but not such a like how is it described in the universal physics, because everything has different spinning.
I don't think there is any static particle. I don't think there is any static particle. It's always dynamic, because it is spinning, or
yes.
See, for example, thermodynamics.
I don't know.
When you say thermodynamics, right?
Yes.
If we go to thermodynamics, okay, thermodynamics of kinetics, thermodynamics of gases. Okay, so this is a fundamental thing. So, or kinetic theory of gases. So you have many particles, suppose in a cylinder. There, what thermodynamics considers is always they keep moving.
But excuse me. That is same is oversimplified concept. It's correct. Yes. How is it? But the space where this particle is moving, the macroscopical space, same has a something. We are same thing. It's empty space, but that is not empty. Is a physical space, and they are this space influencing the moving of these particles.
So this is macro space. This is micro
exactly
space.
Our space or gigantic space. Everything. the space is different, like the microspace, because the microspace particle has their sphere. That is how we have in case of atomic concept something.
Yes.
Example,
So
every time we have to take in consideration most simple atomic form, the hydrogen.
Yes. So the degree, what you call the low degree of freedom. See what happens micro, because they have low degree. So they don't have really think, but microscopic more degree of freedom, higher degree of freedom. So they can do the spinning or vortex.
Exactly. They are spinning, they are moving, the sphere, but where they are in, that this medium also has his physical influence to this particle, because this space are fluctuating. Do you know? Every time we can have imagine of the fluctuation. Example, radio waves is the same fluctuation.
Yeah, fluctuation. Yeah, fluctuation or oscillation.
Okay,
right.
Right, and you have to think in such a situation, because the things the problems appears that the everything is very, very simplified, and we have to try to catch the problem with its real in its real form.
Yes.
It can be simplified. It is existing for once something very, very interesting in nature, that the phenomenon of nature it looks same. They are same, but in every kind of form they are expressing same role in different expression, but the meaning is same. That was used in case of the earthquakes example. In earthquakes can be explained, the phenomena of earthquakes can be explained the stroke, biological problem, stroke of something same.
Yes. Yeah, it has this. Yeah. See, very important. For example, heartbeat, right? It's because the heartbeat occurs because the frequency is slightly different. Slight change in the frequency causes the heartbeat. So there is a mismatch. Otherwise, the heartbeat cannot occur. It cannot be perfectly harmonic. It's not resonant. Then the heart cannot, so become resonant, then it affects the heart. So the heartbeat is very, very important. Heartbeat is slight change in the frequency causes it's to create destructive interference and causes that to beat. So that's life. That's how the life came into being. Without that, there is no life. If it is perfectly harmonic, resonant oscillation, there will be no life. So you need these beats, which beats tells you that there's a slight difference in the frequency, that causes that. So we call it kind of a destructive interference, so that you don't have, perfect resonance. So that's very, very important for the heart. And that is the same thing for the earth also. There could be slight changes in the frequency that causes that beat, that causes all these phenomena. Even so, when they become resonant, that's when it becomes starts to become the earthquake. So the frequencies somehow match each other. They are exactly the same at some magic angle, and they cause resonance, and that resonance causes, lot the explosion. So that's otherwise the frequencies are slightly different. They change ever so slightly, so the earth can show the beat. But become resonant because of the motion of whatever the plates or the magnetic things. Then they come up with a magic angle. Then they create a very high level of resonance, and that's the one that causes explosion. So I think that's very yeah. What you're saying seems to makes a lot of sense. So I'm just explaining in terms of the actual frequency. We know from classical theory also this is true. If you go to classical physics, you see this difference in the frequency. What causes the beating? It's very clear in wave theory. It's a very very important part of wave theory. So if I go here, let me check. I can show here.
But one thing is it's every time you have to count that not only in physics, in geology exist similar problems that everything is oversimplified, and if it's oversimplified, that in case we can catch the meaning of the everything, every phenomena we can catch very well.
Yes.
Exist big mistakes in geological interpretation too. I have found such a situation, and these things can be observed in the physics.
Yes. So that okay, very important point. I think it's a good discussion. We have to continue. What we talked with Christopher and you, we have to amplify. We have to make it bigger, magnify, talk more about this.
Raja, my problem that I didn't evolve my mathematical knowledge, and only this is my problem in your discussion, because I put effort to understand the phenomena in reality, and I did not give attention to evolve my mathematical knowledge.
That's okay.
When I was young in mathematical, but after that I left the mathematics in the direction of the observation of the phenomenological observation and interpretation.
Yeah, I think the physics aspect, observation is very important. I will emphasize that. Mathematics is important to quantify that observation. It's very important.
I know very well. If we know well the phenomena, in such a case we can describe very well with mathematics too.
Yes. So we have to know.
And that is that.
Yeah, my PhD advisor used to tell me that my master's
and that was a problem that I didn't show attention to mathematics, and that is why it was a problem, because when before 30 years ago I lost my job too, and after that I have to try to survive with other methods. Before 10 years I was with very